Hello everybody, today's lesson is going to be about U substitution and integration by parts, and these are both different methods that we can use to make or to find certain integrals. I've already introduced you to the U substitution method if you'll recall, but today we're going to officially incorporate it into our lesson. The U substitution method and the integration by parts can make integration easier, although you can't use them both every time. So different integrals will require different methods of integration, but these are just some really incredibly useful methods that you will stumble upon and have to use to take many different types of integrals. So we're going to go ahead and first talk about the U substitution method. Here's an example, and let me just get my pen ready. Here's an example. It's the integral of 40x times x squared minus 5 to the power of 5. So for the U substitution method, essentially what you're going to do is you're going to take some part of this function and you're going to make it U. Sorry, that doesn't look like a U, but you're essentially going to take a complicated part of your integral and you're going to substitute that all for U. Then you can just plug in this variable and it'll make your integral easier and more simplified. So I'm going to walk you through this one just to sort of show you how to do this. But essentially, when you're choosing your U value, you should choose a part of your expression that when you take the derivative of that part of the expression of that U, then that derivative is somewhere present in the integral. And also, when you choose your U, it should simplify the integral. It should make it easier to actually solve this. So what I mean by this is essentially I have two options for choosing my U. I can make this my U, or I can make this my U. Now, to choose which part of this expression is going to be my U variable, what I should do is I should look to the most complicated part of the expression. So think, is 40x to the power of 1 more complicated, or is x squared minus 5 more complicated? And x squared minus 5 actually, all raised to the power of 5, is more complicated, so it's looking like I'm going to choose this one for our U. But then I should also think, if I take the derivative of this expression of x squared minus 5, is that derivative located somewhere in the equation? So for instance, if I were to make U x squared minus 5, if I were to take the derivative of this, I would get du equals 2x. Remember to do implicit differentiation for this. That's why you have your du and your dx. Essentially, this would be our answer. Now, although we don't actually have this 2 located somewhere, if we rearrange this equation, and you always want to move your constants out of the equation, so this would actually be, if we were to simplify the above, it would be 40 integral of x squared minus 5 all to the power of 5 dx. And this actually, this is our x dx. So the derivative of our U variable is located in this equation, because here we can simplify this. We can make this du over 2, and we see that we have an answer for x dx. So essentially what we're trying to do with U substitution is just choose a U value that you can literally just substitute in, so that when you actually plug in all our variables, you'll get 40 And this I'm going to make, we decided that this is going to be our u. So u to the power of 5, oops, u to the power of 5, and x dx right here, our x dx is du over 2. So essentially what you're doing with u substitution is just trying to substitute in these variables and just simplify the equation. Because now we actually can find the integral of this. If this is just a constant, this is essentially 1/2. So we can also move it outside of our integral, and we would get 40. If I'm doing this over here, we would get 40 over 2 times the integral of u to the power of 5 du. And if we want to simplify this even further, then we'll get our answer to be 20 times, oops, sorry, it's a little bit laggy, 20 times 1 over 6 u to the power of 6 plus c. And remember this plus c because you're doing, it's an indefinite integral. You don't have some, you don't have some a or b value over here, which means that you're going to have to add a plus c. And now what we do is we just plug in our u variable back into the equation. So if we want to simplify 20 over 6, that's 10 over 3 times our u is x squared minus 5 all to the power of 6 plus c. Plus c. So this is what our answer would be using u substitution. Alright, so now we're going to do some other example problems. And I'm sorry if I sound out of it or if I don't sound like myself. I did get my wisdom teeth removed, so it's a little bit weird talking right now. But here's another example problem. We're going to use u substitution to solve this equation. And remember, you should choose a u variable such that if you find the derivative of u, it should be in the equation. So your derivative of u value is in the integral. And you should also make sure that choosing your u simplifies the equation, simplifies your integral. So, with these two things in mind, we should think, what do we want to make our u variable? Now, you might look at cosine of x squared, this whole thing, and think, well, this is sort of complicated, and it'd be nice if I could make this our u variable, right? And that would be nice, but if you were to take the derivative of, this is not actually going to be our u value, but if you're just thinking about using this, the problem with making cosine of x squared your u variable is that if you take the derivative of this, you're going to get sine of something, and you're going to have to use the chain rule, and it's just going to be a lot more complicated. So what you're going to want to do is refrain from trying to make cosine your u variable, because that's not going to work. And instead, look and hone in on this x squared part. Because if you take the derivative of x squared, if you make this our u, if our u is x squared, and our du would be 2x dx. And this is in our equation right here. Because if you rearrange this, then you're going to get cosine of x squared times 2x dx. And so this easily shows you that if you were to use x squared as your u variable, you would essentially get the integral of cosine of u, cosine of u times du. And we know how to take the integral of cosine. The integral of cosine is just sine. So we're going to get sine of u plus c. Remember, don't forget that plus c. And then if we were to plug in our u variable back in, we would get sine of x squared. Sine of x squared. Sorry, that's supposed to be a parentheses. Plus c. And this would be our answer. And notice that if you were to take the derivative of sine x squared plus c, where c is some constant, using the chain rule, you would come back to this, equation up here if you were to find the derivative of this entire thing. So that's just one way to check your answer and make sure that you did this correctly. Whatever you took the integral of, if you find the derivative of your answer, that should be the expression that you were given in the problem. Now we're going to go ahead and do another example problem. We're going to start with this one right here. So look at the most complicated part of the expression and figure out if you can make that your u variable, and if you take the derivative of that variable, is that derivative somewhere in the equation? So if we were to look at, say, this entire bottom part, let's say that you were considering about making this your u. Well, do you know how to take the derivative of the square root of x squared plus 1? Of course you can. That's with the chain rule, right? You can do this, but this isn't actually going to simplify your expression, because what's going to happen is you're just going to get some really complicated derivative, and that complicated derivative is not actually somewhere in your expression. It's not actually in the integral. So what you're going to want to do instead is decide instead to look at just what's in the square root and consider making that your u. Because if your u variable is x squared plus 1 and you find the derivative of that, then you're going to get 2x dx plus 0. And we don't have 2x dx in our equation, but we do have x dx. And we can easily solve for x dx, because if we divide this expression by 2 on both sides, you get du over 2 equals x dx. So now, if you plug in your u variables and your du variable, what you'll get is the integral of, if we wanted to plug in this top part first, what you would get is your du over 2. I'm substituting in the numerator first. Du over 2, all divided by the square root of u. And although this may look complicated, we can actually simplify it even more. And if we were to move out this constant, this, because essentially this is du times 1/2, right? If we move our constant out of the integral, we get 1/2 times the integral of du over the square root of u. And the square root of u is the same thing as writing u to the power of 1/2. So I'm sorry that this is loading, but this would be u to the power of 1/2. And since it's in the denominator, we would make this, we'd make this negative. So 1/2 times the integral of u to the power of -1/2 du. And this would be a much easier integral to simplify. And if we simplify this even further, I'm going to get 1/2 times 1 divided by 1/2 as taking the integral of u to the -1/2. And then this is going to be u to the power of 1/2. So this will essentially cancel out because it's 1/2 divided by 1/2, so this is going to be 1. And don't forget your plus c. So it's going to be the square root of x squared, because this is going to be our u variable. So the square root of u, or the square root of x squared plus 1 plus c. And this is going to be your answer. Now we're going to move on to this next problem, and before we get started with this one, I'm just going to say that both a and b are constants here. So a is some random number and b is some other random number. So don't let this confuse you because it does look complicated, but it's no different from what we've been doing. So what I'm going to do is I'm going to make this bottom b plus sine a of x equal to our u variable, because if we take the derivative of this, we'll see that we get some cosine expression, which we can then use to substitute in our du. And if we get rid of this bottom part and simplify it, then it's going to make our lives a lot easier in terms of actually integrating this expression. So if I'm going to take du, the derivative of this, then, well, if b is just some constant, the derivative of a constant is always 0, plus sine, the derivative of sine ax. And we're going to have to use our chain rule for this one, but the derivative of sine is cosine. So I'm going to get cosine of a of x, and then I have to take the derivative of what's in these parentheses. And since a is just a constant, we're going to get a dx. Now, if we look at our expression again, we see that we have cosine ax dx, and we do have cosine ax dx here, but we also have this a that's sort of interrupting, this constant that's sort of interrupting our expression. So we can easily get rid of this a if we just divide this whole thing by a, so we get du over a equals, this would be cosine a of x times dx. And now we can plug in du over a for our cosine ax dx expression. And if we simplify this, we're going to get the integral of 20 du over a, all divided by the square root of u. And since 20 over a is just some constant, because a is a constant, we can move 20 over a outside of our integral, and we'll get 20 over a times the integral of du over the square root of u. And so we already said that 1 over the square root of u is the same thing as u to the power of -1/2. So we're going to have 20 over a times 2, I'm just skipping a step, but it's the same thing we did up here with integrating our u, And then we're going to add plus c. It's going to be 40 over a, plug in your u, this is going to be, I don't want to write it all out, b plus sine a of s, the square root of that whole thing plus c. And where this squiggly thing is just our u, our b plus sine a of s. I just don't really want to write it all out. But now we're going to move on to integration by parts. So integration by parts is mostly useful for finding the integral of products, of the product of two functions. And you will not always be able to use integration by parts, but there are certain instances in which you will have to use it to be able to solve an integral. So essentially, your integration by parts equation is this. It's your, where u and v are both different functions. So you have the integral of u times the derivative of your v equation, dv is just derivative of v, equals your u function times your v function minus the integral of your v function times the derivative of your u function. And this looks really difficult, but it's not. And the same rules sort of apply for, or the same concepts sort of apply for your u substitution method. The hardest part of both u substitution and integration by parts is choosing what expressions are going to constitute your variables, your u and your v. So with integration by parts, you have to be careful about deciding which function you want to make u and which function you want to make dv, the derivative of the v function. And remember, like, depending on the integral, you may or may not be able to use this method, but there are certainly many instances in which you can use integration by parts to solve an integral. And really this is going to become a lot easier to recognize which method to use for integration with practice. So if you keep practicing it, you're going to be able to quickly identify, can I use u substitution, can I use integration by parts, or some other method to be able to solve this integral. So before I actually get into an example problem, I'd just like to to show you where this equation actually comes from. So essentially, I'm going to derive this equation. We'll just ignore this example problem for now. But if you wanted to figure out this equation, or you want to understand where this equation comes from, essentially, what we're trying to do is take the differential, or the derivative, of the product of two functions u and v. So if I had the derivative of u and v, this is just your product rule. D is just designating the fact that I'm taking the derivative of this product. Using the product rule, we would get u dv plus v du. Because essentially we're taking one function, multiplying it by the derivative of the other function, and then adding that to the other function multiplied by the derivative of the first function. So if I want to find the integral of these two products, I would just simply take the integral of everything here. So taking the integral of u dv plus v du is the same thing as taking the integral of u dv and adding it to the integral of v du. This right here is essentially taking the integral of a derivative, so it cancels out, right? Because if you anti-differentiate a derivative, you're just going to get the original expression. So uv is equal to the integral of u dv plus the integral of v du. And then essentially you would just rearrange this equation so that you would move the integral of v du over to the other side, so that you get the integral of u dv is equal to uv minus the integral of v du. And this is our integration by parts equation. Now, this is where the equation comes from, and now we're actually going to use the equation in this example problem. So essentially what you're going to do is you're going to choose a part of this entire expression to be u, and you're going to choose some other part to be dv. Because we want to essentially replicate this part of the equation, and then we can just solve for our v variable and our du, and then just plug those all back into our equation, and that will give us our answer. So first we have to choose a u, and then we have to choose a du. So essentially we're going to have to find a u variable, we're going to have to choose a u variable, and we're going to choose our dv variable. So the easiest way to go about choosing your u and your dv expressions would be just to think, essentially you're going to have to take the derivative of your u variable to get du, and you're going to have to take the integral of your dv variable to get v. So think to yourself, which part of the expression would be easiest to take the derivative of, which part would be easiest to take the integral of, and if I can take the derivative or the integral of whatever part of the expression, does that actually simplify your equation? So for instance, say that I'm just trying to choose my u variable, and then I decide that I'm going to make it sine of s. And you want to figure out if this is going to work or not. Well, if you take the derivative of sine of s, you're going to get cosine of s. And I didn't leave much room for myself here, but this would be cosine of ds. That's just cosine s times ds. So that would mean that my dv variable would be s ds. Right, because whenever you take the integral of something, it has to be integral of x ds or y dy or whatever variable. So then my v variable is just going to be the integral of s, which is 1 over 2 x squared. Now, if you look at this, you see that your v is now more complicated because you had x to the power of 1, and now you have x squared times some 1/2, and essentially if you plug these variables into this second part of your equation, you're going to get sine of x times 1/2 sine of x, but then you're going to subtract the integral of 1/2 x squared times cosine x ds. And that doesn't actually simplify your equation because you cannot solve for the integral of 1/2 x squared times cosine s easily. So instead, you're going to make your u variable your x and your dv variable your sine of x. So u equals x and dv is sine of x. So then our du is going to be dx, which is much simpler than finding the integral of s, right? Because this is essentially just a 1. And your v is just going to be negative cosine of s. Now if you plug all these into your integration by parts equation, you're going to get the integral of x times sine of x dx equals u times v negative cosine s minus the integral of negative cosine s times du, which is just ds. And we can take the integral of this, right? This is essentially just plus the integral of cosine s. This is just sine of s. So if we simplify this, we get our answer to be negative s times plus sine of s. Of course, plus c. Sorry, I know that doesn't look like an n. So this is your answer that you get from using integration by parts. Now we're going to move on to this next equation. So I wrote the integration by parts equation up here just for reference, and we're going to do the same thing. We're going to choose something to be our u variable and something from this expression to be our dv variable. So we're just going to sort of test run this. Let's just say that you decided to make your u variable s. That means u would be s, so your du would be ds, and your dv would be e to the power of 2s, and your v would be the, well, technically this would be e to the power of 2s ds, and your v would just be the integral of this, so this would be 1/2 e times 2 to the power of s, or sorry, 1/2 e to the power of 2s. So then if you just plug in everything, you get your integral to be u, which is s times 1/2 e to the power of 2s minus the integral of v du and if we just simplify this integral and the rest of this equation, 1/2 s times e to the power of 2s minus, essentially this would be 1/2 times 1/2 e to the power of 2s. So this would be 1/4 e to the power of 2s. And then plus c. And this would be your answer. So now for this next problem, what we're going to do is the same thing. We're going to choose a u variable and we're going to choose a dv variable. So recall that the derivative of ln s is actually just 1 over s ds. So knowing that, it's very simple to just choose ln s as your u variable, because if you take the derivative of this, you get 1 over s ds. So then our dv variable would actually just have to be ds. And if we take the integral of this, then you would just get s. And if we plug everything back into our equation, then our equation is just uv minus the integral of v du. That would be ln s times s minus the integral of v du, or the integral of s 1 over s ds. So you see that these s divided by s, it just cancels, and so you'll have the integral of 1 ds, and the integral of 1 ds is just s plus c. So you're going to have s times ln s minus s plus c. Oops, plus c. So now here is one last example problem using integration by parts. So here, if we were to make our u variable equal to s, then that would mean our dv variable would be ln s. And I know that we just solved for the integral of ln s, but still, that's sort of finding the integral of if dv was ln s ds, then finding this integral is just overcomplicating it. And we did already find it, but if we had to make our v equal to s ln s minus s, this would actually be in our integral, which is not something that we can easily integrate if we were to plug this into our integral of v du. So instead of making dv equal to ln s ds, we're instead going to make dv just s ds. So our u is going to be ln s, and our dv is going to be s ds. So our v is just 1 over 2x squared, and our du is just 1 over s ds. So plugging everything into our equation, it's u times v minus the integral of v du. So that's 1 over 2s squared times ln s minus the integral of v du, so 1/2 s squared times 1 over s ds. So this is essentially just going to become s to the power of 1. So this would just be 1/2 s squared ln s minus the integral of 1/2 s, which is just 1 over 4 s squared plus c. And that's it. Thank you.